Hey, Brianna.
Hi,
How are you today?
I'm doing good. How are you?
Good. So what are we doing in calculus now?
I have a test coming up on the product rule and the quotient rule in that chapter.
Okay. Can
So he gave a,
you want to verbalize the problems, or you want to send me a picture of the problems?
I can send you a picture.
Okay. Let's do that. And while you're sending a picture, just send one picture at a time. Don't send like 4 pictures in one email. It takes too long to get to me. But
Okay.
while we're waiting for that, maybe you could verbalize the first one.
Um, my computer isn't loading the page for a sec. Okay, there we go. So it says find f prime of x for f of x equals 1 over the root of x with no negative exponent.
Like that?
Yes.
Okay. First thing that before you can use the product rule, the variable has to be in the numerator. And radical signs don't work real well. In other words, the very first thing you want to do with all of these is to eliminate the radical sign and then put that variable in the numerator. In other words, if I say f of x equals 1 over x to the 1/2, that's the same thing, correct?
Mm-hmm.
Now put that in the numerator.
So x to the negative 1/2.
Yeah. Now we can use the product rule. You can't use the product rule until your variable is in the numerator. So when you apply the product rule to that, what do you get?
So x times.
Always start there with the exponent. In other words, the very first thing you're going to do on the product rule is start with the exponent and then subtract 1 from the exponent. So that's how you take the first derivative using the product rule.
Oh,
Okay. Now, it would be different if there was a number. Let's say f of x was 2 times x to the minus 1/2. Well, then you're going to take the minus 1/2 and multiply it by the 2. In other words, what we're really doing is taking the exponent, multiplying it by the coefficient, and then subtracting 1 from the exponent. Okay? Now, are there any other parts to this question other than finding the first derivative? How about evaluating the first derivative at some number?
No, it just says no negative exponents.
Okay, so let's write this answer without negative exponents. What would it be?
So it would be negative 1 over 2 times x to the 3 over 2.
Yeah, perfect. And then, of course, that negative sign can go out in front, it can go in the bottom, it can go in the top. They're all the same thing.
Right.
All right. Did you send the page yet?
It says it's sending, but hasn't sent yet.
Okay. How many attachments are there on it? Just one?
Yeah.
Okay. Sounds like it's taking its time. That's all right. You can verbalize them. These don't sound like problems that I need to be looking at. In other words, as long as you can verbalize what f of x is, I can tell you how to figure out its first derivative.
Yeah, they don't get to word problems until the last couple.
Okay.
So this one is find f prime of x for f of x equals x plus 1 parentheses
Parentheses what?
squared.
Still in here. Parentheses what?
Squared.
To the fourth?
To the second.
To the second squared.
Yes.
So x plus 1 quantity squared. Okay? This actually does require the chain rule, although you're not going to see it. You've had the chain rule?
Yeah.
All right. So you've had the key rules, the power rule, the product rule, the quotient rule, and the chain rule. The chain rule, as you no doubt have learned, is the derivative of the outside times the derivative of the inside. Well, let's first of all talk about what is the inside here.
X plus 1.
Yeah, and just for the heck of it, I'm going to list it over here. Okay. Now, what's the derivative of the outside?
Is it
You can use the power rule.
2 times x plus 1?
Start with the coefficient or the exponent, 2 times plus 1, subtract 1 from the coefficient, and now multiply the whole thing by the derivative of the inside. Well, what's the derivative of the inside?
X.
1.
Oh, 1.
Just 1. In other words, when you take the derivative of u, you get 1. So the derivative of the inside is 1. That's why I say that this is using the chain rule, but just barely, because the derivative of the inside is 1. So there's your answer.
Okay.
Got your email? Let me open it up.
Okay.
Did you send this on an iPhone?
Yeah. Is it a little blurry?
Well, you need to send it as a large image, not a small image.
Okay.
When you send it as a small image, this is what happens. When I expand it, I can't read it. If you send it as a large image, it comes out crystal clear.
Gotcha.
So I'm not expert on how the iPhone works, but if when you sent this, if they gave you a choice to send it as a small or a large, send it again, only this time choose large.
Okay.
And then in the meantime, maybe you could verbalize another one.
Yes. Okay. So find f prime of x for f of x equals 2x times x squared plus 1 quantity cubed.
Read it again. For some reason, I'm having a hard time hearing you.
2x times x squared plus 1.
The plus 1 where? In the exponent or down here?
Down there. And then the parentheses, yeah. And then the quantity cubed.
Okay. So, first of all, we can remove the inside parentheses. What do you get when you remove the inside parentheses?
2x cubed plus...
Hold on. Don't apply the exponent yet. Just remove the inside parentheses.
2x
Minus.
minus.
In other words, when you remove these inside parentheses, you have to distribute the negative sign to both terms. So it becomes minus x squared minus 1. Those two are the same. I haven't changed anything. Okay?
Okay.
Now let's do f prime of x. What's the derivative of, well, first of all, what's the inside?
2x minus x squared minus 1.
Yeah. And what's the derivative of the outside?
3 times 2x minus x squared minus 1.
To what power?
The second.
Okay. Now you have to, because there's a chain rule involved, in other words, we do have an inside here, and we have to multiply the derivative of the outside by the derivative of the inside. So what's the derivative of the inside? Which would be u prime.
So 2 minus 2x.
That's it. So that's your answer. And you don't really have to take it beyond that. Sometimes you do, but in this case you don't. In other words, you certainly don't have to expand this. Here, let me point where you can you see it when I point with my cursor? I think you can.
Yeah.
You don't have to expand that, the thing that's squared. And you don't really even have to distribute the 3 to the other part. In other words, we have it in fully factored form. And it's not going to get any simpler by manipulating it algebraically. Let's see if I got your newest email. Not yet.
Yeah, it still says sending on the same thing.
Still sending?
Yeah.
Wow, you got some slow internet access today.
Yeah, I don't know why it says so today.
Okay. Let's talk a little bit about the chain rule.
Okay.
If we have a function that is a function of x, then we can differentiate it. But when there's an inside, it's not a function of x. In other words, in this last problem, what we really had was u cubed, right? In other words, when we made u that inside, or this inside, then now we're looking at f of x is equal to u cubed. Well, you can't take the derivative if that's u unless you apply the chain rule. So f prime of x is equal to 3u squared times u prime. This is the derivative of the outside, this is the derivative of the inside, and when we're done, we're going to convert it back to x's. In other words, if they give you the function in x, you always want to give them the derivative back in x. And this u notation is probably new to you, but
Yeah.
you should get used to it because you're going to be using it a lot in calculus. Probably the rest of the way you use u substitution. It's a very common method of viewing these more complicated functions. I think I got your email. Let me open it up. Yeah, notice the difference. All right, let's see. We did 1, we did 2, we did 3, haven't done 4 yet. Should we do 4 next?
Yeah.
Okay. Just a second, let me get my screen. Now, let's talk about chain rule again.
Okay.
Most of the time, I would say 99% of the time, it's pretty easy to figure out the inside, right?
Yeah.
If I gave you this, what's the inside going to be?
X squared plus 1.
Yeah, and that's the case with most of them. If I gave you this, what's the inside going to be?
E.
Nope.
E to the x plus 1.
Just the x plus 1.
Uh,
Okay? So it's not always easy to figure out the inside. And the two most difficult problems I can think of are these two. If you can understand these two, you've made a lot of progress in figuring out the chain rule. Now, first of all, notice that these are not the same. Sine squared of x means sine x times sine x. Sine of x squared means you take whatever x is, you square it, and then you take the sine of it. So they're completely different. Okay? But if you had to take f prime of the top one, you need to figure out what the inside is. What do you think the inside is on the top function? We'll call it u.
Is it sine?
Sine x. And the reason that's the inside is because now I can write this thing as u squared, which I know how to differentiate. Just have to differentiate the u part, which is 2u, and multiply it by the derivative of the inside, which is cosine x. In other words, if I go over here and list the derivative of the inside, it's cosine x. So it's u squared, or let's do it the way they're probably going to do it in class, which is 2 sine to the 1 of x, that's the derivative of the outside, times the derivative of the inside, which is cosine of x. Okay? Now, the bottom function, what is u? What is the inside?
Sine. Sine.
Notice that if I made it the same inside, sine of x, I would not be able to write this as a function of u. So you don't want to make it sine x as the inside. You want to make x squared as the inside. Then I can write the function as the sine of u, which I know how to differentiate. Okay? So on the second one, what's the derivative of the outside?
Cosine.
Of x squared. In other words, you don't need to change the argument. It's cosine of u, and u is x squared. And now what's the derivative of the inside? What is u prime?
2x.
So I'm going to multiply this thing by 2x, and I'm going to put it in front, just because when you have trig functions and polynomials, if you put the polynomial in front, it's less confusing. Okay? So notice I had to do both of these problems using different insides. And it wasn't at all obvious on what the inside was. So you want to make the inside whatever allows you to differentiate it. In other words, let's talk about another function that's a little hard. What's the inside?
3x.
Yeah, because if I make it e to the u, well, I know what the derivative of the outside is. It's e to the u.
Yeah.
Now, what's the derivative of the inside?
E.
No, this is the inside.
So it's just 3.
3. Okay, so the full derivative is 3, and now I resubstitute for u. In other words, here's the derivative of the inside, or the outside, excuse me. Here's the derivative of the inside. So the quick and easy way to do chain rule is the derivative of the outside times the derivative of the inside. You just have to make sure you can figure out what the inside is, and it's not always easy. All right, let me have a look at number 4. So in number 4, we have sine squared of 6x equals f of x. Do the derivative of the outside first.
So the outside would be 6x.
No. This one, we're going to have a double application of the chain rule, actually. Okay, but if I had to define u, it would be the sine of 6x, because that would make f be, hold on, u squared, right?
Yeah.
In other words, you determine what u is based on the fact, can you differentiate that? Yes. F prime is what? It's 2u, but now you have to multiply it by the derivative of the inside. Well, what's u prime up here? What's the derivative of the inside?
Cosine of 6x.
And there's a second inside. The 6x is inside. So I have to multiply that by 6. So u prime is actually 6 cosine of 6x. So I'm going to multiply this by 6 cosine of 6x. I'm going to resubstitute back, get rid of the u. So now I have 2 sine of 6x times 6 cosine of 6x. My final answer is 12 sine 6x cosine 6x. So this was actually a double chain rule. In other words, we had to figure out what the original inside was, but then there was a second inside. And that's the thing with chain rules, is you can actually have as many insides as you can imagine. There could be 11 insides. And you just take them one at a time and you whittle it down. You find the first inside, and usually this is going to be about as complicated as it gets, where when you go to find the derivative of the inside, you have to apply the chain rule a second time. But it's easy enough to do, because the inside of u is 6x. But the original inside was sine of 6x. And notice why. It's because I can write it as u squared. And I can differentiate u squared. In other words, if I go back to my original problem, where when I had sine of x squared, like that, well, if I were to let u be sine of x, hold on. In other words, if I were to incorrectly let u be sine of x, notice that I cannot write y as sine of x. What is the, I can't write it in terms of u, because that should have been u. And then I could write it sine of u, which I know how to differentiate. But if I let be u equals sine x, there's no way to write this in terms of u. How would you do it? The first thing we have to do is square the x, not square the sine x. So figuring out what the inside is really the only difficulty on these chain rules and stuff. And I really mean that because the quotient rule is just being able to memorize. Product rule is easy enough. Hold on. All right, probably if we just keep doing some, I think you'll get the hang of it. All right. G of x equals sine x tangent x minus secant x. Okay. Now, we don't need a chain rule here. There's no insides. Okay. We've got that, which we're going to use the product rule on. And then we got that, which we're just going to use our derivative of secant x on. Okay, so we don't need the chain rule here. I don't need to define anything in terms of u. Let's talk about the product rule. If y equals u times v, then y prime is the derivative of the first times the second plus the reverse. And that's the best way to memorize. Whenever you have the product of two different functions, it's the derivative of the first function times the second function plus the first function times the derivative of the second function. Okay, so we're going to use the product rule on just this part here. So take the derivative of the first part. What's the derivative of sine?
Cosine of x.
And we're not taking the derivative of the second part yet. Now do the reverse. Now take the first part. What's the derivative of tan x?
Isn't that negative secant x?
Positive secant squared. Oh. Secant squared x is what the derivative of tangent is. And now we still have this part. Okay, so I have to subtract, and what's the derivative of secant?
Oh, that.
It's secant x tangent x. Okay, so there's our answer. And you just do it piece by piece. As long as you know your derivatives of trig functions, and you know your power rule, product rule, quotient rule, and chain rule, then you can always work through these piece by piece. Okay? Let's look at number 6, because number 6 we're going to have to use combination of the quotient rule and the chain rule. Now, you want to know y prime. First of all, let's talk about the quotient rule. If I've got one function being divided by another function, then y prime, there's a real easy way to memorize it. Do you have it memorized? This is the hardest one to memorize. How's it go?
The bottom times the derivative of the top times the derivative of the bottom times the top over the bottom squared.
Great. Almost. Okay. The way I memorize the quotient rule is it begins with the bottom and ends with the bottom squared. And you can't miss it if you remember that only. It begins with the bottom, which is v. Well, I got to multiply that by the derivative of something, so it's u prime. And then it's subtraction, not multiplication, it's subtraction. Remember the product rule was addition. This is subtraction, and that's key because the order matters. And then what goes here is the reverse of what went there. So this must be v prime times u all over the bottom squared. So if you can remember that the quotient rule involves subtraction in the numerator, then is all you have to do is remember it begins with the bottom and ends with the bottom squared. Because if you begin with the bottom, you know it has to be multiplied by the derivative of the top. And then you know that there's going to be subtraction because order matters. And then what you have over here is just the reverse. If this was VU prime, this must be V prime U. Divided by the bottom squared. Okay, so let's apply that to this function. What's y prime going to be?
So 2x squared times 2 times 3x minus 2.
You do have to apply the chain rule to this part. In other words, you're taking the derivative of the top, which is 2 times 3x minus 2, but now times the derivative of the inside. What's the derivative of the inside?
3.
Okay. Now, minus the reverse of that. So what's the reverse of that?
So
Here, let me do it like this so I don't have to, yeah.
okay.
I don't want to make it more confusing than it is. So the first thing we did was the bottom times the derivative of the top.
So then,
Now we know it has to be subtraction because I cannot do these in either order like you can the product rule. Notice the product rule, you can do uv prime plus u prime v, but that's the same as u prime v plus uv prime. So you can actually do the product rule however you want. I really do suggest that people do it the same way every time just because it makes for fewer mistakes. But you can do it in either order. Not so with the quotient rule. Quotient rule has subtraction going on in the numerator. So you have to do it v u prime. And then the next one is going to be v prime u. Well, what's the net rest of it?
minus 4x times 3x minus 2 squared.
Yeah, and don't worry about expanding that. Just don't. Just trust me. In other words, most of the time you're not going to have to expand those. That's a perfectly fine way to present it. Okay. Now what goes on the bottom?
2x to the 4th.
Well, it's the bottom squared. What is that number when I square it? Got to square the 2 and you got to square the x squared. So it actually turns into 4x to the 4th. Let me write that. 4x to the 4th. Now, let's do a little simplification. Here's the thing about the quotient rule is quotient rule isn't particularly hard. What's hard is all the algebra involved. And there's a lot of complex algebra involved. So let's first of all simplify that. How does that simplify? And by simplify, you don't need to distribute everything, but you can certainly distribute the numbers. We got a 2 times a 2 times a 3. So at least 12. I got an x squared And then I got 3x minus 2. Okay? Now, I'm subtracting 4x times 3x minus 2 squared. And I'm going to divide it all by 4x to the 4th. Well, can I do anything with the numbers? The 12, the minus 4, and the 4?
I think you can factor out 4x.
Yeah, you're right. I can divide every term in the numerator by 4x, and I can divide every term in the denominator by 4x. Okay? What that gives me is 3x instead of 12x squared, still times 3x minus 2, minus, we divided by 4x, so this just becomes 3x minus 2 squared. And when I divide the bottom by 4x, I get x cubed. Okay. So I'm simplifying it gradually. Now, the easiest way to handle the numerator. There's 2 ways to handle it. I could distribute the left side of it, and I could square the right side of it. And notice that's going to be useful because when I distribute the left side, I get 9x squared, and that's going to be the very first term I get when I square the right side. So my 9x squared is going to disappear, so it's definitely worth doing. So let's do it that way. That's the way that's going to be the most understandable. So I'm going to distribute the 3x, so I get this. And then I'm going to leave that in parentheses for a moment, and I'm going to square it. And that becomes that. Okay, you with me?
Mm-hmm.
And I left the parentheses in there because they're significant. In other words, if I don't have those parentheses, I don't have the same answer. Now the next goal is to get rid of those parentheses. What do I have to do to get rid of the parentheses? I've got to distribute this negative sign to every term. So let's do that. So lose the parentheses, what have I got left?
Minus 9x squared plus 12x minus 4.
Okay. Still all over x cubed. Now I can do quite a bit of simplification in the numerator. In other words, the 9x squareds cancel. I got a total of 6x minus 4. And in the denominator, I still have that. And there's not really much I can do more at this point. Could factor out a 2 from the numerator, but it doesn't really do any good. In other words, if I factor out a 2, I'm not able to simplify anything. And when you're not able to simplify it, there's no point in factoring it out. So this is a perfectly acceptable answer. Or this,
Okay.
or that, but there's no reason to go to that step unless maybe I had a 2 in the denominator. Notice if I had a 2 in the denominator, then it would be worth factoring out that 2 because then I could cancel this 2 with the 2 in the denominator and simplify it further. So you really only factor out and expand if you see that you can do stuff. In other words, I didn't necessarily have to expand this term right here. But I could see that I was going to have a 9x squared and a 9x squared over here. Let's go ahead and expand it because I know I can simplify.
Okay.
Okay, and that's the general rule you always want to use. Now, that we covered a lot for just 6 questions.
Mm-hmm.
In other words, you can't really do justice to the power rule, product rule, quotient rule, and chain rule with 6 questions.
Yeah.
2 of them trig questions. So typically you would spend 2 weeks in class on these 4 rules, and they would probably have you do 20 to 30 problems, just so you could get used to doing power rule, product rule, quotient rule, and chain rule.
Oh, cow.
Okay? In other words, you're not going to get expert on it by doing these 6 problems.
Yeah.
And the next thing they're doing is implicit differentiation, which is fine. Implicit differentiation is not really that hard, conceptually or otherwise. Let's do it. And let me explain it a little bit. So there's our equation. Okay. And the question says, what is dy dx? Well, with explicit differentiation, everything starts with y equals something. And everything on the other side is x. So it's really easy to just apply the rules of differentiation explicitly, because the left-hand side is y. But when you're using implicit differentiation, that's not the case. Notice that this function, you can't solve for y.
Yeah.
So we need a different technique for coming up with dy dx. And what we're basically going to do is take dy dx of both sides of the equation. Calculus is just like algebra. Whatever you can figure out to do to the left side of the equation, you can do to the right. And that includes differentiation, it includes integration. Hold on 1 minute. My dog always goes off in my session. I don't know why I just don't close my door to start with.
Mine does the same.
Now, implicit differentiation is actually very easy. If I'm going to differentiate the left side with respect to x, that's the way I'm going to write it. And the rules are simple. If I run into an x variable, then I differentiate it explicitly. If I run into any variable other than x, for example y, then I differentiate the outside, but I always multiply it by dy dx. Okay? So if we do this term by term, what's the derivative of that?
4x.
Yeah, and you could even say that I'm going to multiply this by dx dx, but that's 1, so I don't need to write it.
Okay.
Okay? Now, I got multiplication going on there, so I'm going to have to use the product rule. So let me put parentheses around it. Okay. Now, take the derivative of that.
That would be 2x times y plus x squared times dy dx.
What is dy dx when y is the variable? What's the derivative of the outside? 1. Yeah. In other words, if I'm taking the derivative of y, I'm taking the derivative of the outside, which is 1, but then I'm going to multiply it by the chain rule, which is y prime. Or I can write that dy dx. Don't need to write the 1, but I do need to write the dy dx. because I ran into a variable that was not x. If I'd have run into an r, then I got to follow it with a dy dr. If I'd have run into a t, I would have to follow it by a dy dt. So if you run into a variable that is not the denominator, you always have to follow it with the chain rule, the derivative of that new variable with respect to x.
Okay.
Now, put that in parentheses because we did the product rule for that. And now what's the second, the very last term? What's the derivative of that?
2 dy dx.
2y times dy dx. In other words, you still have to take the derivative of the outside. The derivative of the outside was 2y. But because it's a y, I got to follow it with a dy dx. Now, what's the derivative of the right side? 10 was what was over there. What's the derivative of 10? 0. Okay. Now, notice how we're going to solve for dy dx. We've got a dy dx here. We got a dy dx there. So, and this is where it gets a little tricky. You want to move every term that does not have dy dx on it to the other side of the equation. Okay? First of all, I want to get rid of these parentheses. Don't need them anyway because that was all being added. So I've got this term that has a dy dx in it. I've got this term that has a dy dx in it. I'm going to leave that on the left side of the equation, and I'm going to move everything else to the right side. And you'll see why here in a minute. 4x does not have a dy dx. Move it over there. That does not have a dy dx. Move it over there. Okay? Now, this is the hard part, the part that people have a hard time seeing. Trying to solve for dy dx, what can I do?
Divide.
Factor dy dx out of both terms on the left. And that's the key. There's always a factoring involved here. What's left over is x squared minus 2. This is now all equal to this. Now the final step is to divide both sides by that. I can think of that as a coefficient. So dy dx, the answer that they're looking for, is minus 4x minus 2xy all divided by x squared minus 2. So this is the answer. Now, the one thing that's very different between explicit differentiation and implicit is when you explicitly differentiate something, you always end up with answers that have nothing but x. When you implicitly differentiate something, you frequently have both x and y in the answer. Like we do here, we have x and y. That's fine, nothing wrong with that. And I can't really simplify that. There's nothing I could take out. I guess I could factor out a 2x, but that doesn't help. In other words, it doesn't allow me to simplify anything. So I'm not going to do it. And that's, like I said, that's my criterion for whether I should continue to try to factor or not. Let me just show you why that doesn't help. In other words, if I take the numerator and I factor out a minus 2x, well, what am I left with? I'm left with 2 plus y, and I still have in the bottom x squared minus 2, so I can't do anything to simplify that further. Because of that, I wouldn't even go to the trouble of factoring out that minus 2x. If I had a 2x in the denominator, well then that'd be different. Then I would go ahead and do it because I can cancel it out. So how much algebra you choose to do kind of depends on whether you can simplify it further. In other words, I can certainly see doing this step, not knowing, maybe I can simplify it if I factor out that minus 2x. But then when I look at the answer, I realize, well, no, that doesn't help. I can't do anything with this expression. Can't do anything with the 2 plus y, and I can't do anything with this x and this x, because this is x squared minus or plus a number. So I cannot divide top and bottom by x. Okay, and this would be dy dx. And this is actually one of the tougher problems, not a problem that I would have started with implicit differentiation, just because you've got to handle the product rule also. Let's see, we don't have much time. Let's take an easier one. Excuse me, I keep wanting to do that. I don't. Let's talk about the equation of a circle. Right? That's a circle at the origin with a radius of 4. Now, find dy dx. So we'll call this, actually this is the equation. When I say find dy dx, what I really mean is take the derivative of the left side with respect to x, and then take the derivative of the right side with respect to x. Well, what do you get on the derivative of the left side?
2x plus 2
plus what?
y, 2y times dy dx.
Right, and I'm going to call that y prime, just in interest and brevity. Okay, what's the right side? 0. Derivative of any constant is 0, regardless of what you're differentiating it with respect to. Okay, now solve for y prime. What's the first? Do what?
2x from both sides.
Okay, so I got this. And the next step?
Divide both sides by 2.
By 2y. Remember, I'm trying to isolate y prime. I'm trying to solve for dy dx, which is y prime.
Okay.
So I got this, and I'm dividing it by 2y. Now I can cancel those 2's. So my final answer is x over y negative. That's what dy dx is for this problem. Now, the reason I like this problem is because it's relatively straightforward and there's no product rule or chain rule or anything to apply.
Right.
Okay? Now, let's go back a moment. And yeah, we got enough time. Usually where you're using implicit differentiation, you're not really differentiating with respect to x. Most of the time, you're differentiating with respect to t. Okay? Just trust me on that. You'll find out why. But that's where implicit differentiation is absolutely required, is when the variable is t, and t is usually time. Okay? Now, differentiate this thing with respect to t.
So 2x plus y squared.
Hold on. We ran into a variable that was not t. Therefore, you have to follow with dx dt plus 2y dy dt. And the derivative of the right side is still 0. Okay? Now, this problem, the question was not solve for dy dx. The question was just implicitly differentiate it with respect to t. In a real-life problem, they would then probably give you dx dt, and they might give you dy dt, and they would maybe give you y, and the problem would be solve for x, okay, which you'd be able to do. But the simplest way to remember implicit differentiation is exactly this. If you run into a variable that is not your denominator variable, then you always have to follow it with dx dt or dy dt. Or if I had another variable, r squared, in there, then I would have to follow that with dr dt. If I ran into a t squared, that's the only variable where I would just have to differentiate it, and I would not have to follow it with a dt dt. Although you could certainly think of it as doing that, it's just that that's always 1. So the way I think the best way to memorize implicit differentiation is you just do each variable, and if that variable is different than this denominator variable, you have to follow it with a d of this variable relative to dt.
Okay.
And now, unfortunately, I have a 4:30, so I can't do any more of these. Second derivative is actually pretty straightforward. You know how you take the second derivative? Is you take the first derivative and then you take the first derivative of the first derivative. That's always the way you find second derivative, every single time. There's no way to jump from function to second derivative. You have to take the first derivative, and then whatever you get, take it a derivative of that again.
Okay.
Okay? The main thing about all of this calculus is really the algebra. The algebra is what's tough. You saw on some of the problems we did that the algebra was pretty complex. And that's the nature of it. And particularly when you're using the quotient rule, the algebra tends to be really complicated. And I'm talking not algebra 2, I'm talking college algebra. In other words, you need to be up on your algebra skills.
Okay.
And in fact, if you ever have to take the second derivative of a function that's got a quotient to begin with, wow, that's a 20-minute problem, and you really need to be up on your algebra skills. You need to know how to factor really well, you know how to simplify really well.
Yeah.
Okay, so we'll end it with question 7. And I don't know, you have a test, or is this just homework for tomorrow?
Yeah, I have a test on Monday.
You have a test on Monday? Okay. Well, you want to schedule another session between now and Monday? We could finish the rest of these.
Yeah, sure.
Okay. All right, Brianna. Nice talking to you again. You have a good weekend, and I'll talk to you next time.
Awesome. Thank you.